Hello everyone, I'll be talking about elliptic curves today, and it's a very vast area of research, but let's see if we can understand the fundamental ideas. So let's start by looking at what an elliptic curve is. An elliptic curve is any curve that satisfies this equation. There are a couple of other variants and a longer form of this equation, but this is a reduced form. It's called the Weierstrass equation or the Weierstrass form of an elliptic curve, and that's y square equals x cubed plus ax plus b, and it has to satisfy this condition: 4a cubed plus 27b square should not be equal to 0. And this condition comes from something called the discriminant. This is the discriminant for cubic equations, just like b square minus 4ac is the discriminant for quadratic equations. If this condition is not obeyed, we end up with unusable curves, so curves that are not differentiable at some point, or curves that intersect themselves, or curves that are not useful for cryptography in any way. So elliptic curves have a lot of interesting properties. Let's look at some of the more basic ones. The first important property is symmetry about the x-axis. So if you look at the equation here, we see that if we replace y by minus y, the equation still holds. So what this means is that if I can say a point x comma y lies on the elliptic curve, I can also be sure that a point x comma minus y also lies on the elliptic curve. Any line intersects a curve at 3 points, and this includes multiplicities, which means that a point can appear in this set of 3 more than once. And this comes from this general theorem that generally the number of common zeros equals the product of degrees of the polynomial. So the degree of an elliptic curve is 3, the degree of a line is 1, and therefore there are 3 points to the intersection. And what about tangent lines? So we'll discuss this in more detail later, but we can assume that the point at the tangent line has a multiplicity of 2, and therefore the line, and I'll explain why later, but if it has a multiplicity of 2, that means the tangent line intersects the elliptic curve at exactly one other point. Right? That's all we have to remember. We'll come back to it later. So now I say that if we include one other operation on these group of points, we can turn it into a group, which is an abstract algebraic structure. We can turn the set of points of an elliptic curve into a group. And why do we need to think in terms of groups? Why is it useful to turn the set of points on an elliptic curve into a group? And the reason why abstract algebra is so useful is because of this important principle. If we can prove that something is a group or any other abstract algebraic structure, we get a lot of other properties at like a package deal. So we can analyze a lot of different supposedly unrelated things the same way. And I'll give you a small example. We don't have to understand this in too much depth. I'm simply introducing it to make a point. But let's look at signals and ordinary vectors. Both form a vector space because they both follow the axioms of a vector space. And let's look at this. I mean, the process of Fourier analysis is breaking up a signal into its component sine and cosine waves, just like the process of vector decomposition is a process of breaking up a vector into its basis vectors. And the operation that we look at is the dot product in the case of vectors, and the operation we look at is the inner product in case of signals, sine and cosine signals. And these are two completely unrelated fields, but simply because they both form the same abstract algebraic structure, we are able to manipulate them, treat them the same way mathematically. And so that's why it's useful to think about groups, rings, and fields whenever possible, because that will allow us to analyze a lot of different things the same way. Now that I've made a case for thinking of things in terms of groups, let's go ahead and do it. Let's look at what a group is. 3 important points to note in a group. A group is primarily a set. It's a collection of entities, and it's associated to some operation using which 2 elements can be combined. And the set of entities along with the operation follow 4 properties or axioms. And the 4 properties are closure, associativity, existence of identity element, and existence of an inverse element. I'm assuming everybody is already familiar with these. This is kind of an add-on point. It's just another terminology. It's also called an abelian group if it satisfies commutativity. So along with these 4 properties of a group. So now let's go back to our original point. We were thinking about turning the set of all points on an elliptic curve into a group using some operation, some identity element, and some inverse element. So let's see how we decide those things. The operation here is called elliptic curve point addition, and it's defined like this. We start with 3 collinear points on an elliptic curve. So I have created a small demonstration. So this is what a typical elliptic curve looks like. We can vary a and b, and all of these are valid elliptic curves except if the discriminant is not 0. So we start with 3 collinear points, p, q, and r. Let's go ahead and declare them. P, this is q, and they have to be collinear. So we draw a line through p and q, see where it intersects the curve, and call this point r. Right, this is our collinear point. And now, this is how the group law is defined. P plus q plus r equals 0e. 0e is the identity element, which is the 0 supposedly for this group, and the reason why I haven't used the normal 0 is to distinguish it from the number 0 and the origin of the coordinate axes. It is neither of those. It's for now let's just think of 0e as some identity element, some abstract identity element for this group, and plus is just the symbol that denotes elliptic curve addition operation. In this case, when p, q, and r are elliptic points, plus does not stand for ordinary addition. It stands for some special operation that we'll define soon. But the identity element and the operation work together in this way: p plus q plus r equals 0e. And it's important to, I'll explain this next, but this operation, elliptic curve point addition, is purely defined geometrically. Even when we write out the equations, we see that the only way we get the equations is by doing whatever we do geometrically, except using coordinate geometry, the same equations we learned in grades 11 and 12. The same equations, whatever we do geometrically, we do algebraically. So let's actually try to define the group operation and the 0 element, bearing in mind this law. What would the operation have to be between two elements? What would p plus q have to be, and what would the identity element be, and therefore what would the inverse have to be if this law is to be satisfied? Okay, let's look at that. First, let's look at the inverse element and the identity element, because they're very closely related. We say that the identity element is a point at infinity, and the inverse of x comma y is x comma minus y, and this is just a reflection of x comma y across the x-axis. Now the point at infinity is it doesn't actually exist. It's something like a mathematical construct. It's defined like the point at which all lines parallel to the y-axis intersect, and this is very similar to the concept of in ray optics. If you remember, we learned that all parallel light rays meet at infinity, and it's not that they actually meet. It's just something of a mathematical construct that we use to simplify our equations. And this point at infinity works the same way. And the inverse is a reflection across the x-axis. Let's look at a small illustration, what this actually means. What if I took 2 points that were the inverses of each other? So this is approximately a straight line, a vertical line, and can I say that q is the inverse of p? I can, because they're reflections across the x-axis, and the inverse just becomes x comma minus y. And we see that this only intersects the curve at 2 points. It doesn't intersect the curve at 3 points. And this is a problem because we need to be able to define a group structure on the set of all elliptic curve points. And so the way we do this is by defining some point at infinity, which is again it's somewhat loosely defined. It's defined in order to meet the condition of the group law. So we say that there's some point at infinity, and if we include that point too, then we technically have 3 points that this line passes through, and with the condition that q and p are inverses of each other. Oh, and one more quick thing: if I have a point p, I can denote its inverse as minus p also, because plus is the symbol that we use for denoting the group operation. So minus would simply mean perform the group operation except with the inverse. So let's see so now we have an idea of what the group operation is. We have an idea of what the identity element and of what the inverse is, and let's see if we can define the group operation from those. So you remember the equation p plus q plus r equals 0e. If we transpose r, this becomes p plus q equals 0e minus r, and of course that's just equal to p plus q equals minus r, right? Because anything added to the identity element is the element itself. And so what this means is that in order to add two elliptic curve points P and Q, we find the third collinear point R and we take its inverse. And so in this situation, it would look something like this. We draw a line through P and Q, we see where it intersects the curve, and we reflect that point along the x-axis to get minus R. So this minus R is what we get when we perform the group operation between P and Q. We draw a line, see where it intersects, reflect. What happens if P equals Q? So now it's technically true that an infinite number of lines pass through the same point. So let's see what happens when we bring P and Q closer and closer together. I had to define this as a piecewise function because it wasn't letting me plot implicit functions, so let me just change that. Right, so what happens if we bring P and Q closer and closer to each other? What happens is that the line becomes closer and closer to the tangent line, and we know that the tangent line passes through one other point in the elliptic curve, and so we find that point and we reflect it across the x-axis. So that's precisely what it means to add a point with itself. If P equals Q, if you want to compute P plus P or Q plus Q, we take the tangent at that point, see where it intersects the elliptic curve, find that point and reflect it across the x-axis, or find its inverse. And that is the sum. That is the sum, elliptic curve sum to the group operation. Right, and now this is the algebraic form of elliptic curves. There is nothing special happening here. It looks very mathematical, but if we follow the same geometric procedure that I outlined in the previous slides, and we implement it using coordinate geometry, we end up with these equations. So let's not spend too much time on this because it's not very difficult to derive on our own too once we've properly understood the process. Let's look at what scalar multiplication is in elliptic curves. Scalar multiplication follows regular logic. N dot P is performing the group operation n times. So we have a point P and we perform the group operation n times. This plus is not regular addition and this dot is not regular multiplication. They are both specific to elliptic curves. N dot P means perform the group operation n times. So now we come to adapting elliptic curves to cryptography. We know that computers need discrete units to work with, so let's see how we bridge that gap. So the first thing we need to do is restrict the curve to a finite field f of P. Let's not go too much into depth of what a finite field is, but for now let's just assume that they're a group of whole numbers. And so what we do is we start with a regular elliptic curve, just like what we have seen, and when we restrict it, we get a set of points that follow this condition. X comma y both belong to this f of P, and so now we see that we've ended up with a set of discrete points. Each of these x and y are whole numbers, and they satisfy this equation. The equation we see here is it's a mathematical definition of an ordinary elliptic curve, the one we see on the left, plus the point at infinity. Right? We see x comma y belonging to r square equals this is the equation, and this is the constraint, and this is the point at infinity. And this is the restricted elliptic curve. Both x and y belong to the finite field. This equation except on the finite field, the constraint except on the finite field, along with the point at infinity. That's all that it means to restrict an elliptic curve to a finite field. And do we have to redefine point addition? Do we have to redefine our idea of inverse or identity element? No, we just have to modify it a little bit. A line on a finite field looks slightly different. Instead of extending off into infinity, we cycle back, just like the elements. We take mod P for, instead of y equals mx plus c, we have y equals mx plus c mod P. So it sort of repeats. And just like our ordinary group operation, we find three collinear points, and if you want, we find a point through P and Q, we see where it finds R, and we find the inverse of R. But when we find the inverse, we change it a little bit. Instead of the inverse of x comma y being x comma minus y, it becomes x comma minus y mod P. But this inverse, or what we get after we find the inverse, is P plus Q, the group operation. The algebraic equations are exactly the same except with a mod P at the end of each one. There's absolutely no change there. And these are the same equations that we saw that came as a coordinate geometry application of the geometric process that we saw. So now we have to get a little mathematical. There's a lot of information on this slide, but let's understand the principles in isolation, as in just as mathematical principles, and then in the next 1 or 2 slides I will tie it in with elliptic curves. So for now, let's deviate a little bit and focus on these as pure mathematical principles first. So groups can be cyclic or non-cyclic, and we say a group is cyclic when it has this pattern. For some element A, if we raise A to successive powers, then we end up forming the whole group. And when I say raise to successive powers, it doesn't mean actual multiplication, it just means perform the group operation that many number of times. And for a particular number of times, we get the identity element. Such a group is called a cyclic group. A would be called the generator, and N is called the order. We'll define it a little more rigorously afterwards, but these are what these variables stand for. And a subgroup is a subset of the group that also forms a group with the same group operation. So what I'm saying is that we have a group is essentially a set of entities, a collection of entities. We take a subset of those entities, points, groups, numbers, whatever. We take a subset of those elements of the set, and if those elements, if that subset of elements also follows the same 4 axioms of a group with the same group operation as its superset, then we call it a subgroup. That is all that a subgroup means. So let's look at a small example. This is a group of whole numbers from 0 to 9, and we define the group. Let's define the group operation to be addition. So I make the statement that this set is a cyclic subgroup with generator equals to 2. So let's start from the perspective. Let's tie this in with what we've seen here. I'm starting with generator 2. What does that mean? 2 plays the role of A here, which means I should be able to compute 2, 2 power 2, 2 power 3, 2 power 4, 2 power 5, so on. And when I say power here, again, it's not ordinary multiplication, it's performing the group addition, which in this case is addition. That's what the group operation is. So 2 would just be the number 2. 2 squared would be 2 plus 2. 2, okay, or sorry, I should say 2 power 2 equals 2 plus 2. 2 power 3 is 2 plus 2 plus 2, and so on. So if I actually write it out, we will see that 2 is, of course, 2 is 2. 2 plus 2 is 4. 2 plus 2 plus 2 is 6. 2 plus 2 plus 2 plus 2 is 8. And now when we go to 2 power 5, or 2 plus 2 plus 2 plus 2 plus 2, then we see that we actually get 10, but this is a finite group with modulus with order 10. So we take modulus 10 with everything. So 10 modulus 10 is 0. And so now even if we do 2 power 6, we get 2, 2 power 7 is 4, 2 power 8 is 6, 2 power 9 is 8, and so on. And this is, so we see that we can start with some point, call it a generator, and we can generate a cyclic subgroup from it. And now here's an important question. If we take any point of a group, I have some finite group like this, f10, f20, f30, I have any finite group, and I take some point and I treat it like a generator, as in I raise it with successive powers, does it always create a cyclic subgroup? The answer to this is yes, it does, because of the closure property of groups. So the element of the group A, it belongs to the group. If I perform a group operation with any element including itself, it will give me another element from the same group. And so no matter how many times I perform the operation, the group operation with this element, I will always end up with an element in the set. And the only way that is possible for all powers is if it is a cyclic subgroup. Okay, so that is a very important point. If I have a finite group, I take any element, I treat it like a generator, and I say I will generate some cyclic subgroup from this. I'll just, raise it to successive powers, get the output each time I raise it to the successive power, and put each of those outputs in a set. That set will form a cyclic subgroup of some order. Okay, let's look at which, we'll worry about which order later, but every element of a group, if treated as a generator, will generate a cyclic subgroup. That's an important point. Now let's define the order of a group a little more rigorously. The order of the group is some n such that n dot p equals identity element, and again n dot p is the same as raising to the power n. It means we perform the group operation n times, and p would be the element of the group in this case. And in this situation, what is the order? We say that the element 2 has order 5 because the smallest number n such that the generator 2 will give the identity element is 5 after 0, of course. So 2 power 5 will give us 0 again, and so the order of, we see how an order is associated to the generator here. 2 is technically a member of this group of order 10, but we say the order of the point 2 is 5, and that's because the cyclic subgroup generated by 2, which 2 of course can generate a cyclic subgroup because it's an element of the group, the order of the element 2 is 5, which is the order of the cyclic subgroup generated by that element, right? So that's the definition of an order. This is a very important point. Every group of prime order is cyclic, which means that each element is a generator, and this comes from Lagrange's theorem. So Lagrange's theorem for subgroups, it's a very simple theorem. It just says that the order of the subgroups, the order of the subgroup of any group divides the order of the group. So if I have some group, it has a cyclic subgroup. The order of the cyclic subgroup is a factor of the order of its superset. So what happens if the order of the superset is prime? What would the order of the subgroup have to be? Again, the order of the subgroup divides the order of the group, and if the order of the group is prime, then the order of the subgroup has to be either 1 or the prime number itself. If it is 1, what does that mean? What does it mean when the order of a group is 1? Well, it means that even if I perform the group operation once, I will end up with the identity element, and the only element for which that is true is the identity element itself, right? Because if you perform the group operation once, you end up with the identity element. So either the generator that we have chosen for the subgroup, which of course that's the same subgroup we talk about when we talk about order of the subgroup being a factor of the order of the group. The generator we have chosen for that, if the order is 1, will be the identity element. But for any other element, the order of the subgroup is the same as the order of the group. And if the element has to generate only elements within the group itself, because of closure property, if the generator has to generate elements within the group itself, and its order is the same as the order of the group, that means it has to generate all the elements of the group. So it's a little, I know it's a little dense, it's a lot to take in, but if you think about it, it will make sense, I assure you. So let's just recap whatever we are supposed to take away from this slide, and I'll integrate it with elliptic curve theory next. But the important points in the slide are what a cyclic group is, what a generator is, what a subgroup is, the fact that every element of a group, when treated as a generator, will generate a cyclic subgroup, and the fact that every group of prime order is cyclic, which means that each element of a group of prime order is a generator for that entire group of prime order. Okay, so now let's see how that fits into elliptic curve cryptography. We know that the restricted elliptic curve is itself a subgroup of the overall elliptic curve E, but the order of this restricted elliptic curve is not necessarily P. That's just the order of the finite field. But again, if you go back to the equation, we'll see that the only condition for the restricted elliptic curve is that both x and y must belong to the finite field. But the restricted elliptic curve can contain any number of points, and the order of the restricted elliptic curve need not be a prime number, even if small p is a prime number. And we call the order of the restricted elliptic curve n, and it can be calculated using an algorithm which we won't discuss too much. It's enough if we remember that there is a way to calculate capital N from knowing the restricted elliptic curve. So ideally n should be prime, but the commonly used curves cannot have prime numbers. So the reason why cryptographers and mathematicians love working with prime fields is because of the principle I showed you above. Every group of prime order is cyclic, which means each element is a generator. So what that means is that if I had one element of that group and I had the prime order of that group, that means I could generate the entire group from just those two numbers, which you can see how that would be a huge advantage. We don't really need a lot to define the entire group. And so it would be great if capital N was a prime, but the commonly used curves, which are chosen that way because of security or because of ease of some other computation that's required, they don't have a prime value of capital N. So what mathematicians do is they take a subgroup of even the restricted elliptic curve. So the restricted elliptic curve is just a set of points, but that itself is also a group. It's a subgroup of the overall elliptic curve E, and therefore it also follows all the group properties, and therefore we can take any point from this restricted elliptic curve and it will form a cyclic subgroup. Why? Because we proved that any point in a group, if we take any element in a group and we use it as a generator, it will generate a cyclic subgroup. That is a very important principle. So what we do is we take a subgroup of the restricted elliptic curve, and that subgroup will be of prime order. Why prime? Because, as I said, there are a lot of advantages to working with a prime field, because all we need is one element of that prime field plus the prime order, and we can generate the entire field. So what we want to do now is that we have the restricted elliptic curve and we want a subgroup of that by picking one element and using it to generate a cyclic subgroup. So that's exactly how it works. We take a point P, which is an element of the restricted elliptic curve, and it's also a generator for its own cyclic subgroup, which let's say it has some order n. So mathematically it looks something like this. No matter how many times we do the elliptic curve point addition, it will always follow this pattern. And again, this is the same definition we saw for order, n dot p, or if we do the group operation with p itself n times, then we end up with the identity element. And this is an important point. The order of the subgroup is different depending on which point we start with, but always a factor of n, a capital N, which is the order of the restricted elliptic curve. So let's look at this piece by piece. The order of the subgroup of the restricted elliptic curve. What is the subgroup of the restricted elliptic curve? That is what we get when we take a random point on the restricted elliptic curve and we treat it as a generator, and we generate a cyclic subgroup from that. And the order of the cyclic subgroup that we get will be different depending on which point we start with. So some point P, it might cycle after 2 powers. Another point might cycle after 11 powers, but that would mean that capital N is some multiple of both of those. So in this, of both of those orders. Why? Because of Lagrange's theorem, the order of the subgroup divides the order of the group, and therefore conversely, if you have 2 possible subgroup orders, then the order of the group should have both of those as a factor. So if I have a subgroup of order 2 and a subgroup of order 11, then that would mean that the order of the group has to be 22. Or if I had one subgroup of order 2, one subgroup of order 7, one subgroup of order 11, that means that the order of the overall group, the larger group, would have to be 2 into 7 into 11, which is 154. Right? So that's how this works. Now the next step is deciding a base point. So the way we do this is by deciding the subgroup order first, the prime order, and then we try to find a generator point that gives us a subgroup of that order. So the process is extremely simple. We start from a restricted elliptic curve, which has a group of order capital N, as we discussed. We find a number called the cofactor, which is equal to capital N divided by n, and we know this will be a whole number because of, again, Lagrange's theorem, which is that the order of the subgroup, which is small n, is a factor of the order of the group, which is capital N. So let's not focus too much on this point, but h is generally 1, at most it's 8, and this is because we don't want the overall group to be composed of multiple different subgroups of different order. So it's best if h is 1, although it can also go up to 2 and 8. So we choose a random point p on this restricted elliptic curve. So for better security and better computation, it's not always random. There's some thought goes into choosing this starting point p initially, but theoretically it will work with any point p. And we calculate h dot p, which is this dot again refers to scalar multiplication of an elliptic curve. So we perform the group operation with p itself h times, and this point g is the generator for our cyclic subgroup. And so in order to understand this process, let's look at it this way. To see why this works, look at n dot h dot p, and let's focus a bit on this first. I say that capital N dot p equals 0. Why? Because this is how we define the order of the group. This should be 0e, but this is how we define order of the group. And the order of, so we can start with some point p, and we saw that it generates a cyclic subgroup of some order, and that cyclic subgroup has an order which is a factor of capital N. So even if you do it capital N times, we'll still end up with 0. It's the same thing that we spoke about when we talked about the subgroup of 2, subgroup of 7, subgroup of 11 example. So even if the subgroup was, even if we had to take a subgroup and take its generator and perform the operation 154 times in that example, we would still end up with 0. Right? And so this is true. N dot p equals 0. And n dot p can also be written as n dot h dot p, because capital N equals small n times h. Which means, so if we compare this to the definition of order, all this is saying is that there's some point h dot p for which n is the order. It's the generator point for which n is the order, and h dot p gives you a cyclic subgroup of that order n. Right, so it's very straightforward. It's probably a lot to digest at the beginning, but it's very straightforward to understand. And now we look at what we need to uniquely define a elliptic curve cryptosystem. There are 6 different values that provide a fingerprint for an elliptic curve, and these are called the domain parameters. So let's look at each of these 6 individually. First is a prime number that determines a finite field, that is small p. The second 2 are parameters of the actual curve a and b. The third is a not so random point on the curve. I mean, theoretically it could be any curve, any point, but it's chosen with some care. And then the order of the cyclic subgroup, which is small n, and the cofactor of the cyclic subgroup, which is small h. Now we are moving closer and closer to classical cryptography now. Let's look at what the elliptic curve discrete logarithm problem is. Let's start with the ordinary logarithm problem, which is this. A and b are members of a finite field. Given this equation, a power k mod p, is there an efficient way to find k? It turns out this problem is very hard to solve, and a lot of cryptography is built on this. So this is kind of like a one-way function. Given a and some k, I can find b, but given a and b, I cannot find k. In elliptic curves, there's a exact analog. N dot p equals g. P and g are 2 elliptic curve points. Even if someone knows p and g, is there an efficient way to calculate n? And it turns out this is much harder, supposedly, for elliptic curves. The elliptic curve DLP is much harder, and that is what cryptography is built on. And let's see how this principle is used for Diffie-Hellman key exchange. So again, the same way, let me cover ordinary Diffie-Hellman key exchange, and then we'll go to elliptic curve Diffie-Hellman key exchange. So the principle here, again, it looks a little difficult to digest, but these mod p's, all they're supposed to stand for is the fact that all of these happen on a finite field. And so what the point that I'm trying to make here is to say that g power a power b equals g power b power a on a finite field, and this turns out to be true. So given this principle, let's look at the process. let's say we have Alice and Bob who want to settle on some secret key. They come up with two secret numbers A and B. They need to come up with a secret shared number. So they agree on two public numbers G and a prime number P. Why prime? Again, because cryptographers love working with prime fields, because of the reasons I said. They have a lot of advantages. And G and P are both public. Anybody can know those. So Alice has A. Alice comes up with A. Bob comes up with B. Alice computes G power A mod P. Bob computes G power B mod P. So far so good. Now they exchange these numbers over an insecure channel. So Alice sends G power A mod P. Bob sends G power B mod P. And an attacker cannot retrieve A and B from these, even if he has G and P, because of the discrete logarithm problem. Right? So right now they're secure. And now what Alice does is, whatever she receives from Bob, she blindly raises that to the power A on the same finite field, and she gets some value S. Bob does the exact same thing. He receives something from Alice, and that's something he raises to the power B over the finite field. And so now we see that they've landed on the same secret shared number because of this principle that G power A power B equals G power B power A on the same finite field. And the point of this whole exchange was that if we notice, Alice and Bob never had to reveal A and B to each other. They came up with two random, completely secret numbers, and using some protocol, securely they've landed on some secret shared key that no other person knows, and no other person can possibly calculate it, because he would have to know both A and B in order to do that. And so let's see how this works out for elliptic curves. It's almost the exact same thing in elliptic curves, except instead of modular arithmetic, you have elliptic curve arithmetic. A dot B dot P equals B dot A dot P, and turns out this is true. And remember, A and P are numbers here. So this is ordinary numbers, 1P, 2P, 3P. A and B could be ordinary integers. And so there's a multiplication sign here. This is ordinary multiplication. Dot is scalar multiplication in elliptic curves. Right, and the principle is A dot B dot P equals B dot A dot P. Alice and Bob come up with two secret numbers A and B. They need to come up with a secret shared point, so they agree on two public numbers G. They agree on a base point, which is analogous to agreeing on two public numbers, and everybody knows this base point. So Alice computes A dot P, Bob computes B dot P, and they exchange these numbers over an insecure channel. Technically, it should be they exchange these points, because A dot P gives a point, B dot P gives a point, which are two coordinates. So they exchange these numbers over an insecure channel, and it won't affect security because it is impossible to retrieve A and B from whatever Alice and Bob send. That is the ECDLP. So Alice, whatever she receives from Bob, she takes that and she computes A. She takes the scalar multiplication of A with whatever point she receives, and she gets S. Bob does the same thing. He receives something from Alice. He takes the scalar multiplication of that point, and he gets S. And we see that both of them have started with a random number, and they have a public point. Everybody knows this point, and still they've managed to settle on some secret shared key. That is how the Diffie-Hellman algorithm works. And once they have these secret shared elements, they can do whatever. For example, you can represent it in hex and then encrypt, or you can feed it into some kind of key scheduling algorithm, anything. But the key point is that they've settled on a common value now, simply by generating some random numbers and keeping it private. And this is all done securely because of DLP. Okay, so this is one of the last topics, public and private key generation. A public key cryptosystem it's useful to think about it as a technology template. So as long as public and private keys satisfy some properties, which I will spell out after this, they can be used for a wide variety of applications. So that's like signature, authentication, confidentiality, anything. And how elliptic curves are useful here is because they help with the key generation. So let's look at the conditions first. A public key and a private key, let's not worry about how they're used, let's just worry about how they're generated and what relationship they need to have. A public key and a private key association should be unique. So it's generally achieved by generating a public key from a private key. So what we're seeing here is that there should be an association between a public key and a private key, and because everybody can access the public key but nobody should be able to access the private key, we say that the public key should not reveal any information about the private key. And so let's look at this equation, G equals n dot p. We say that p is public information, everybody has it, and so our only variables are G and n. Out of these, which one should be the private key and which one should be the public key to satisfy these? The answer is, well, we should be able to generate the public key from the private key. Are we able to generate G from n or n from G? Because of the discrete logarithm problem, it is impossible to generate n from G. So we have to generate G from n because P is public knowledge. And so G is the public key and n is the private key. So these are two other quick applications I'll mention for elliptic curves: factoring of large numbers and testing whether a number is actually prime or not. And this is actually a very popular method for a primes of more than 1000 digits. And this is my source. I don't know much about these, so I had to provide a source. Right, so let's look at a comparison of two popular schemes, ECC and RSA. These are a set of different elliptic curves, and by different elliptic curves I mean they have different domain parameters, which are the 6 values that we spoke about earlier. They kind of fingerprint an elliptic curve, and this SECP256K1 is the elliptic curve used for Bitcoin and Ethereum. And this, what this table says is, what it says is, if I have an elliptic curve of key length 256, it is of comparable security with this a similar crypto system, an RSA crypto system with key length 3072. So now we can see that elliptic curve, and this is a big reason for why elliptic curve cryptography is now so popular. It's because we can use we can achieve the same level of security, comparable levels of security, much more efficiently. So thank you for listening. Hope you guys enjoyed it.